Okay, Chapter 0, Section 8, Solving Basic Equations. Okay, in this section, we're going to look at solving linear equations, solving power equations, and solving one variable in terms of another. The value of the unknown that makes an equation true are called solutions or roots of the equation. And the process of finding solutions is called solving the equation. Two equations with exactly the same solutions are called equivalent equations. To solve an equation, we try and find a simpler equivalent equation in which the variable stands alone on one side of the equal sign. So here are the properties that we use to solve an equation. In these properties, A, B, and C stand for algebraic expressions, and the symbol, this little double-sided arrow, means is equivalent to. Okay, so for instance, we have that if A is equal to B, then it's equivalent to A plus C equals B plus C. So essentially what we've done here is we've added a C to both sides. You're allowed to add the same quantity to both sides of an equal sign. The second property is that if we start with A equals to B, then we're allowed to add a product. We can multiply by C to both sides, as long as C does not equal to 0. So that if A equals B, then we can conclude that C times A equals to C times B. Okay, so we can add the same quantity to both sides of the equation, or we can multiply the same quantity to both sides of the equation. Solving linear equations. A linear equation in one variable is an equation equivalent to one of the form ax plus b equals to 0. Where a and b are real numbers and x is the variable, right? So there's a lot of letters running around, but keep in mind that x is the independent variable and a and b are just constants. They represent numbers. So a linear equation will be something that can be manipulated to fit this form. So here are some examples to illustrate the difference between linear and nonlinear equations. Okay, so on the left-hand side here, we have several examples of things that fit the form of a line. Remember that a line is something that can be rearranged to fit the form of ax plus b equals 0, right? Where the only independent variable is the x, right? So all of these are written in x. So we just have to confirm that each one of these things can be written that way. So for the first one, this one, very close, right? All we have to do to make sure that it fits this form is subtract 3. So if we subtract 3 from this side, subtract 3 from that side, we'll end up with a 0 on the right-hand side. And so we'll end up with 4x. We'll end up with 4x minus 8 equals 0, and that of course fits this form, right? Ax plus b. So definitely the equation of a line, right? The second one can also be manipulated to fit that form. All we have to do is bring everything to one side, set it equal to 0. So here I would subtract 1/2 x from both sides of the equal sign, 1/2 x, and then also add let's put it in blue, add a 7 to this side, add a 7 to this side, and so we would end up with 2x minus 1/2 x plus 7 equals, and then on the right hand side everything would cancel, we'd end up with a 0. And then 2 minus 1/2 as a mixed number, that's 1.5. 1.5 copies of x as a mixed number, plus 7 equals to 0. And then 1.5 we can turn into a fraction as 3/2 x plus 7 equals to 0, right? And so that also fits this form, ax plus b, right? So definitely the equation of a line. The third one, likewise, the third one here, we can rewrite just a little bit. I'm going to rewrite it as x minus 6 equals to 1/3 x instead of x over 3. And then again, if we just bring it all to one side, we'll see that we can set it in that form. So subtract 1/3 x from this side, subtract 1/3 x from this side. 1, right? There's a invisible 1 right there. 1 copy of x minus a third, right, gives you 2/3. So it'll be 2/3 x minus 6 equals 0. And once again, we have this form, right? So all three of these, 1, 2, 3, all three of these are linear equations that can be rewritten and made to fit this form. Okay, what about the other side? Okay, on the other hand, these fail to be linear equations for a variety of reasons. Number one, well, of course, this is a quadratic. It has power 2. There's no way to rewrite this in a way such that it becomes a linear equation, right? Since this is power 1. So this one, on the other hand, fails again because there's a root in there. This doesn't have a root. So there's no way to manipulate this and fix it to make it look like that. And likewise, this one also fails because it has a 1 over x, which is different from x over 3, right? So don't forget that when we have x over 3, this can be written as 1/3 x. On the other hand, this one can be rewritten as 3 times 1 over x, right? This one, which then is equal to 3x to the minus 1 power. So again, that just doesn't have a way for us to simplify it and make it fit this form. One way to simplify it to get rid of that is to multiply both sides of the equal sign by x. So if we have 3 over x minus 2x equals to 1, we could choose to multiply everything on the right-hand side, everything on the left-hand side, both of them by an x. So multiply by x, multiply by x. And we can distribute the x now, and so we would end up with 3. These x's would cancel. And then x times minus 2, we end up with minus 2x squared equals x. And now if we bring this over to the other side, set it equal to 0, we end up with minus 2x squared minus x plus 3 equals 0. So again, not a linear equation. We end up with a quadratic. So sort of a quadratic in disguise if we manipulate it. But still, it's just not a linear equation. So in this section, we're not interested in these yet. We'll worry about that later. For now, we're just focused on linear equations that fit this form. All right, so let's look at this example. We have 7x minus 4 equals to 3x plus 8. So the first thing I'm going to do is I'm going to move all the terms that have the variable x onto one side and all the terms that don't have the variable x on the other side. So I'm going to subtract from this side minus 3x minus 3x. That'll result in a 4x. I'll bring down the minus 4 equals to 8 since 3x minus 3x cancel out and 7x minus 3x becomes 4. Now I'm going to add plus 4 plus 4. Now that gives me a 4x. This becomes 0 equals 12. And now I'm going to multiply both sides of the equal sign by 1/4 to isolate the x. So 1/4 times 4x, that's going to cancel out the 4's, multiply this side by 1/4, and so we get our desired result. Here we end up with x, since the 4 and the 1/4 cancel to become 1. And here we end up with 12 divided by 4, which equals to 3. Good, so here is our answer, x equals to 3. We can easily check it. Check. So if it's true, then that means that when I replace the x with this value, I should get a true statement. The left side should equal the right side. So 7 blank minus 4 is equal to 3 blank plus 8. And we're hoping that 3 is the given solution. So 7 times 3 is 21. 21 minus 4. And 21 minus 4 is 17. Whereas on the other side, we end up with 9 plus 8. And 9 plus 8 is indeed 17. So it worked out. We found an answer. There's more than one way to organize all of this. As long as you abide by the rules, you can get to the answer in a variety of different ways. Some people might have chosen to move everything to the right-hand side, maybe subtract 7x from both sides. Or some people begin by moving everything to one side, setting it equal to 0, and then simplifying it from that perspective. It's all good. As long as you show your work and someone can reasonably follow with what you did, you should get to the correct answer. Let's see what your author provided as a solution. So your author did something very similar, added 4 to both sides, began by adding 4 to both sides, subtracted 3x from both sides, multiplied by 1/4. Okay, similar process. And again, you can check your answer to confirm that you have the correct answer. Solving power equations. Linear equations have variables only to the first power. Now let's consider some equations that involve squares, cubes, and other powers of the variable. Here we just consider basic equations that can be simplified into the form x to the power of n equals a. Again, remember x is the independent variable, n and a represent constants. So equations of this form are called power equations and can be solved by taking radicals of both sides of the equation. The power equation x to the nth equals to a has the solution. Okay, so x equals to the nth root of a if n is odd, and it has plus or minus the nth root of a if n is even. Right? If n is even and a is less than 0, the equation has no real solution. Here are some examples of solving equations. So if we have x to the power of 5, notice that this is a case where n is odd. Right, so here we have this little guy right here. That's this. So n is odd, so it fits this form. N is odd, and so to solve it, we take the 5th root of both sides. Yeah, write that down over here. So if we have x to the power of 5 equal to 32, we're going to take the nth root, the 5th root of both sides. So x to the 5th, you take the 5th root, take the 5th root, and so here the 5th root of x to the 5th becomes x, so just x equals this, which we know is equal to 2. Okay, and of course we can check it. Of course, 2 to the power of 5 does equal to 32. Okay, if n is odd like this, notice that we only get one answer, just the 2. If n is even, then we end up with 2 answers. So for example, if we had x to the power of 4 equals 81, then when we solve this, there's going to be 2 solutions. When we take the 4th root of x to the 4th equal to the 4th root of 81, then x equals to 3 is an answer, right? We can check it. 3 to the power of 4, well, that's going to be 3 times 3 times 3 times 3. These two become a 9. These two become a 9. So the whole thing equals to 81. So in fact, that is true. That is an answer. But of course, there's another answer as well. Notice that negative 3 to the power of 4 is also equal to 81, right? We have negative 3 times negative 3 times negative 3 times negative 3. There's 4 of them. And so these two, negative times negative equals a positive. And so these two become a positive. So these two become positive 9. And these two become positive 9. So that also gives you positive 81. So that's what this thing is telling you right here, that when n is even and the value inside the root, the argument inside the a in this case, is greater than 0, greater than or equal to 0, then there are 2 answers, right, as we noticed here. So what happens is that we have to introduce this plus or minus. When we choose to take the even root of both sides of an equal sign, then we have to notice that in fact there are two answers, the positive and the negative. So we write it this way. There's plus or minus 3 is the answer. Right? Just noting that there are two possible answers. That's what this thing is referring to. Of course, now if we have an even root and the a is also negative, then we don't have a real solution. So for example, if we were trying to find x to the power of 2, it's an even root. We're going to take an even root of both sides, and this equals, say, negative 25. And then we go about our way of trying to find the square root x squared equals to the square root of negative 25. That's what this last case is referring to. If we have n is even, yep, n is even. Here's even to 2. And the a is negative. So now the a is negative right in there. Well, then we don't have a solution, right? There is no such number such that when you square it, the answer is negative 25. This leads into imaginary numbers, and for now, we are not dealing with imaginary numbers. We're sticking to real number solutions. So that's what this is saying, that there is no real solution, no real number solution, only an imaginary solution when we have an even index of our root and the argument inside the radical, the a in this case, is negative. Okay, so if it's odd, then we only get the answer. Also notice, by the way, that we're allowed to have a equal to negative if we have an odd one. So going back to this guy over here, if we had x to the power of 5 and we had negative 32, then we can just go through the same process, take the fifth root of both sides, fifth root of negative 32, and we're allowed to have this. The odd, we're allowed to have an odd index here. There is a number such that when you multiply it by itself 5 different times, the answer is negative. And so in this case, the answer is just going to be equal to negative 2. Negative 2 raised to the 5th power does equal to negative 32. Negative 2 raised to the power of 5 does equal to negative 32. There are 5 copies of negative 2. 4 of them become positive, right? Every 2 cancel out to become positive. And there's still one remaining one, which gives you an answer of a negative 32. Okay, so when the index is odd, then it's just the answer. Take the nth root of both sides. That might be a positive or a negative answer. When the index is even, then we got to take the nth root, but then also notice that there's a plus or minus case we have to introduce. Okay, so here's a couple of examples. Say we wanted to solve each of these guys. For this one over here, what we want to do is isolate the x squared first and then take the root of both sides. So I'm going to move this onto the other side, and we end up with, let's put a plus 5, plus 5, plus 5. And so we end up with an x squared equals to 5. And so now we take the square root of both sides. X squared equals 5. And we're going to take the square root of this side, the square root, let's make it green. Then we're going to take the square root of this side, the square root of this side. And because it's an even, that's how I know I have to introduce a plus or minus. And so I end up with x equals to plus or minus the square root of 5. Now, there is a nice, pretty answer for that, so we just leave it alone just like that. Okay, we can check it by plugging in a root 5 into this original equation. So blank squared minus 5, this is my check, must be equal to 0. And so now if I replace the x variable with a positive root 5, that's going to work out because root 5 squared is just going to be 5, and 5 minus 5 is 0. And if I instead put in a negative root 5, well, same thing, because the whole thing is getting squared and the negative becomes a positive, so it works out. Either plus or minus, the plus or minus case, both of them result in a true statement. Okay, what about this one? It would be tempting, I think, to go ahead and FOIL this out. I think that's the first thing people want to do. They expand this and they get an x squared minus 8x plus 16 equals to 5. And then maybe move this over and kind of work that way. But you don't want to do this. Well, it's just there's an easier way to do this. That can lead to the correct answer, so it's not wrong. It's just that you're missing out on an opportunity to simplify this right away, because we can get rid of this squared here by taking the square root of both sides right away. So if we do that, we end up with x minus 4 parentheses squared equals to 5. So if I take the square root of this side, the square root of this side, again, it's an even one. That's when I know to introduce a plus or minus. On the left-hand side, the root and the power cancel, so we end up with x minus 4 equals to plus or minus root 5. And now all I have to do is plus 4 plus 4. And now all I have to do is add 4 to this side, add 4 to this side, and that gets me to my answer. X minus, and that gets me to my answer, x equals to 4 plus or minus root 5. Okay, again, we can place it right in here in order to double check that our answer does work out. So let's check it. Blank minus 4 parentheses squared should be a 5. And so one solution could be 4 plus root 5. So that works out. The 4's cancel, and then I end up with root 5 by itself. Root 5 squared is 5, so 5 equals to 5. So that would work out. On the other hand, if I put in a for minus root 5, like this, well, the 4's still cancel out. What remains is a negative root 5. And negative root 5 squared still becomes positive 5, so 5 does equal 5. Either way, we have a true answer. Okay, solving for one variable in terms of others. Many formulas in the sciences involve several variables, and it is often necessary to express one of the variables in terms of the others. So in this next example, we solve for a variable in Newton's law of gravity. So here is an example involving Newton's law of gravity. In physics, all of these letters represent something. Force, gravitational constants, the mass of object 1, mass of object 2, the radius, they have meanings, but in terms of the math, they're just variables. So in this case, maybe you're asked to solve for m. So in math, we have the luxury of not really worrying what the variables represent. We're just going to focus on the arithmetic to solve for this particular letter. So keep your eye on the ball and notice that capital M is different than lowercase m. So we have to be careful with our notational style. Sometimes we go back and forth between capitals and lower cases. I see people writing down A, and then the next line they write down A, and they mean the same thing because they're both A, but they do mean different things. So we have to be careful to write down either capital or lowercase when we want to. Okay, so to solve for m is very easy. There's a variety of ways in which you can do this, but I'm just going to take the approach of rewriting it this way. This is the same thing as g over 1, right? G and g over 1 is the same thing. And I'm going to separate this fraction as m over r squared times capital M, or capital M over 1. Good. That way I can recombine these. So I can just say that this is capital G lowercase m divided by r squared times m. And now, keeping an eye on what I want to solve for, right? I want to focus on solving for capital M. What I'm going to do is I'm going to multiply both sides of this equal sign by the reciprocal of this fraction, so that they cancel out to give me a 1, thereby isolating the m. So I'm going to put it in green here. So I'm going to multiply. I'm going to copy this down. M r squared times capital M. And I'm going to multiply this by r squared over g m. Whatever you do to one side, you must do to the other. So I must also multiply this side by r squared over G, oops, see, I did it myself. This is capital M, lowercase m. Don't do that, be careful. So this is lowercase m. All right, so now G, M, each of these things cancel. The G cancels with that, the M cancels with that, the R squared cancels with the R squared. So all of this just becomes one giant 1 times M, capital M. So you've isolated your capital M. And on the left-hand side, well, you could just multiply all this together, and I would get capital F R squared divided by GM, right? And so just to clean it up, the answer is capital M equals FR squared over GM. I did it again. M. Lowercase m. Okay, so here is the solution provided by your author. Very similar to what I did. All right, so hopefully this is enough to help you with this section, and you can complete your homework. If you have trouble with anything, please let me know. Send me an email or come by one of my online office hours.